Hello and welcome to Passive House Accelerator Live. This is actually our season finale of the 2024-2025 season of Passive House Accelerator Live, and the lives take a break during July and August. So we are very pleased to have Ed May here with us today to close out the season and to bring in this season finale. My name is Zach Semke. I'm the director of Passive House Accelerator, and Passive House Accelerator Live is where we bring people together to explore how to make our buildings more resilient to the impacts of climate change and also to mitigate the impacts of climate change. So we're very happy to have you here today. And I am so excited to introduce Ed May. Carmel Pratt is typically the host of the Next Up series of the show, but she has another engagement today and is unable to join us. She's sad to miss it, so I'm here in her stead. So Ed May is a licensed architect and a LEED Green associate. He received a Bachelor of Fine Arts from the University of Massachusetts at Amherst and a Master's of Architecture from Parsons, the New School. Ed has been an adjunct professor at Parsons, as well as an industry professor at Stevens Institute of Technology in Hoboken, New Jersey. In addition, Ed teaches with Passive House Academy, the North American Passive House Network, and Passive House Canada, and is certified by the Passive House Institute in Germany and the Passive House Institute of the US, now known as PHA, as a certified Passive House consultant. He's an expert in residence in the Reimagined Buildings Collective and an instructor in the collective. And I think that he's probably taught many of the people who are on this call. He is an amazing person and very inspiring. So we're very happy to have you here, Ed. And with that, please take it away.
Well, thank you, Zach, and thanks to everybody for attending. Thanks for having me here. Thanks for the invitation to talk. So I'm glad to be with you. As Zach said, my name is Ed May, and I'm going to be talking today about some of the modeling work that we're doing in our office around, broadly speaking, modeling for thermal comfort, modeling for what we might broadly term resiliency, and talk a little bit about how it's affecting some of our design decisions. So it's sort of a whole set of different things that we'll be showing, stretching back several years, which is hopefully interesting and hopefully is a little bit useful for those of you working on passive house projects in the US and Canada. So let me go ahead and share my screen and we'll kick things off here. Let's see. All righty. Are you able to see that okay? Yes, okay, getting some thumbs up. All right, fantastic. Okie doke. So let's get moving. For those of you on the East Coast of the US currently, I am sorry. I am not there, but I'm there in spirit. I feel bad, and I know what a terrible experience it is. As a sort of context for everything that we're going to be talking about in this sort of seminar here, I just want to highlight the role and problem of overheating and cooling. I know in passive house world, we almost always start our discussions by talking about the heating side, about the winter time performance side, and that is important. That is crucial, especially on a total energy performance sort of basis. The wintertime heating energy use is super, super important. But from a thermal comfort and a human experience perspective, I want to make the argument here in this talk, and I think this has been borne out in a lot of our work, certainly in a place like New York City, that cooling and overheating are as big, as important, if not maybe a little more so when it comes to how people really experience the buildings that we're working on. So right now, if you're watching this in the future, there is a terrible heat dome over most of the eastern United States. 250, 230 million people are currently in 90 or 100 degree Fahrenheit temperatures, which will stretch on for a while. I think it is going to break soon, but not at the moment. But that, of course, is just the immediate problem of like today. We know that broadly speaking, and all those of us on this call here, we don't need to go into a ton of depth on the context here. We all know that the impact of climate change is driving up temperatures across the globe. And specifically, what we're seeing is that a lot of the hottest places are getting hotter. A lot of the hot summer nights, for instance, are getting hotter. And we're seeing these types of temperature increases broadly across much of the US and Canada. Not everywhere. There are places that are experiencing some interesting declines in their sort of peak temperatures, but mostly what we're seeing, this from just a few days ago, and a story that popped up in on the news showing some of the nighttime temperature increases between 1970 and 2024, talking about the hottest summertime nights getting much, much warmer, these in degrees Fahrenheit. So we know as a sort of broad a change that our summers are getting hotter, our summer nights are getting hotter, our summer temperatures are getting more extreme. We know that right now in much of the US, people are suffering under a heat dome. And we know that we as Passive House designers are charged with designing not only the most energy efficient buildings, but also buildings that are, for lack of a better term, resilient against these types of effects, against these types of problems or challenges. Now, for those of you working in the Passive House world, you know that Passive House prioritizes a small set of things. So Passive House as a framework is much more focused, much more targeted than some of the more totalizing green building standards out there that might touch on water and touch on energy and touch on embodied materials and material toxicity. Passive House is much more focused, and it's focused on operational energy performance, peak loads, and what they call, or what we call, thermal comfort. And thermal comfort, we'll kind of get into it in this talk here. It's an interesting topic, so I can kind of talk about it all day long. It might be boring for some folks, but I find it quite interesting. The experience of people in our buildings, and so to my mind, quite important. In Passive House world, at least on the PHI side, one of the main ways, or the main way that we quantify and evaluate summertime thermal comfort, talk about the difference between winter and summer. Summertime thermal comfort is by measuring what we call the frequency of overheating and the frequency of excessively high humidity. And so these are metrics that we use to evaluate the building and say, are we predicting that the building is going to perform badly on these kind of rough metrics? Now, there's nothing wrong with these metrics per se. These are excellent high level sort of first order assessment metrics. If you're failing these, you can be pretty confident that you're going to be having a problem with your building. But what I want to argue is that these metrics are, maybe never were, but I think no longer sufficient and adequate for the types of buildings that we're building. And so what I'm going to argue here is that we need to supplement, not eliminate, but supplement. We need to add some new types of modeling and assessment to these existing tools that we're already familiar with working as Passive House practitioners. So my opinion, and this is just my opinion, so feel free to disagree and argue with me. My opinion, after building umpteen bazillion Passive House models over 15 years now, is that the Passive House tools, the modeling tools, they don't push us, they don't incentivize us as designers to be careful enough when it comes to overheating risk. Again, that's my opinion. I believe that we need to supplement, again, not replace, not eliminate, not get rid of, but supplement these existing Passive House modeling tools with other tools so that we can effectively design out the types of overheating risk that we are seeing in some Passive House projects. And not to put too fine a point on it, but lest you think I'm making this up, we do hear regularly from many other practitioners, many of our own early clients, that overheating in the Passive House buildings that we design is and has been a problem. As a result of some of those early, what I might even go ahead and call failures, 2009, we were designing buildings that we didn't quite understand the nuances of all of this, and we definitely designed some buildings that overheated. Those early failures have caused us to become much more conservative and much more careful when it comes to overheating risk. And I want to argue that you should be careful as well. So how do we do that? How will we do that? And what do I think we need to supplement? What do I think is missing from the existing passive house models that I think we should see in the newer generation of modeling tools that I'm recommending that we add? Well, the main culprits, the main issues that I think are present in the existing modeling tools that I think lead us to, I want to say, I don't want to use the words right and wrong, but unhelpful results are number one, that our passive house models are single zone. So single zone models, especially when you get into really large buildings, buildings with heterogeneous use types, really tall buildings that are highly stratified, really spread out buildings. These types of single zone models are just not adequate for capturing the localized overheating that happens in highly glazed rooms, north versus south side rooms, et cetera. So the single zone nature of our models is fundamentally a problem that we need to wrestle with. I think also that while the monthly time step of the passive house models is perfectly adequate for energy performance assessment, it's fast and easy-ish to execute when it comes to doing design phase assessments. It's great for certification. That monthly time step is not quite adequate, again, to wrestle with or to capture the nuance of localized overheating events. There's some other things that are in regard to the models. None of these are like deal breakers. Again, I'm not saying to stop using passive house models. What I'm saying is we want to take these models, understand the nuance of these models, and then add to them some new techniques, some new tools, some new ideas. Before we get to that, let's talk a little bit about thermal comfort. So how do we as engineers, as designers, measure thermal comfort? It's kind of a weird idea. Thermal comfort is your or my experience of a place. But of course, since we're engineers, we want to take that subjective experience and turn it into a number. And so we'll talk a little bit about some ways that we quantify or we turn that sort of lived experience into a value that we can measure and optimize for. But broadly speaking, we can say that your and my experience of thermal comfort within a space are driven by a whole bunch of different criteria. So, of course, air temperature and humidity. Those are maybe like the top two that most of us are already quite familiar with. Those are the ones that we see like on the nightly news. I shouldn't say that anymore. I mean, is nightly news even still a thing in 2025? I think I don't even, I may have just dated myself. When I was growing up in the 1980s, there was a thing called nightly news, and they used to show you the weather, and they would tell you the air temperature and the humidity level. But in addition to the air temperature and humidity level, of course, there's things like the velocity of airflow. So what is the air flowing across your skin, right? Our skin transpires, and we have evaporation of sweat off of our skin that takes heat away from our body. The velocity of air across our skin is going to increase that evapotranspiration, and it's going to cool us off. So the velocity of airflow is really important. The temperature of the surfaces and the space that we're in is incredibly important. Whether those surface temperatures, and we'll come back and talk about that a little bit more, are cold or hot, those are going to strongly affect our perception of comfort as well. And then things like our clothing level. So are you in a full three-piece suit or are you in a bathing suit? Your activity level. Are you playing basketball or are you sitting around in your underpants watching TV? Your age, right? As we grow older, we often become more susceptible or more sensitive to heat, as well as when we're very, very young, infants and very small children, very sensitive to extreme heat. Our gender, our body type, where we grew up, our expectations, and then some other sort of psychological things like, do you have independent control over the space? Do you have the both physical ability and sort of cultural authorization to get up and open the window? Like, is that within your ability to control? That can actually affect how we perceive thermal comfort within a space. So again, what we're talking about here is your and my perception, our feeling. But again, because we're engineers, we want to turn that feeling into a number. So how do we do that? How do we turn your feelings into numbers that we can measure and optimize for? There's two basic standards that you want to refer to if you're interested in any of this type of modeling as a starting point. I'll talk about some other sort of interesting new work that's coming out, but probably the two sort of core fundamental documents that you want to have in your document library are going to be the ISO 7730 and the ASHRAE standard 55. And these are kind of like mirror documents. They're like basically saying the same thing, except one of them is in ASHRAE language, one of them is in its ISO language. They basically outline the same procedures for evaluating and measuring, quantifying the subjective thermal comfort experience of a human being within a space. And specifically, they outline a calculation methodology for determining what we would call, or what is termed in these documents, the predicted mean vote, the PMV, predicted mean votes. This is a vocabulary term that's useful in thermal comfort land for doing this type of modeling. Again, this is a way of taking your and my feelings and expressing it as a series of numbers. And so the way that this index works is the value 0 represents sort of perfectly neutral, one of those like chambers that people go in where they're like completely at the same temperature and you have no feelings. I don't know, whatever the term for those is. But then negative values represent cold experiences and positive values represent hot or warm experiences. And this PMV calculation takes into account all of the things that we were just talking about. Well, not all, but most of the things that we were just talking about: air temperature, relative humidity, airspeed, metabolic rate, that is your activity level, your clothing level, and your mean radiant temperature. Uh, Mean radiant temperature. That's a weird term. You would be forgiven if you have not heard that term before. What is the mean radiant temperature, the temperature experience of the person within the space? Well, if you were to look around with infrared goggles, like those kind of like Predator goggles from the movie, and you were able to see into the infrared spectrum. So if you had a different type of eyeball that was able to see into the infrared spectrum, what you would see is that every solid object around you, the floor, the wall, the chair, the window, the roof, these objects are emitting infrared radiation. So every object that's above absolute zero is going to emit infrared radiation to a greater or lesser extent. The amount of infrared radiation emitted by these solid objects is going to vary depending on the temperature, the heat content of that object. The hotter the object, the more infrared radiation is emitted. Now, our bodies experience this radiation. We can't see it. Our eyeballs can't see into the infrared spectrum. We have sensors, we have cameras that can see into the infrared spectrum, but our eyeballs cannot see into the infrared spectrum. But our bodies experience that radiation within a space. So whether the surfaces around our bodies are warm or cold are going to be one of the important factors that drive our experience of thermal comfort. Now, this is the main or one of the main evaluative criteria when it comes to providing thermal comfort in passive houses in the winter time scenario. So historically, this has been one of the main focus areas or research areas within the passive house community, passive house framework, has been focused on this radiant temperature asymmetry, in particular, the effect with regard to cold windows, very large cold glazing surfaces. And a lot of the early research from the early 2000s coming out of Darmstadt was focused on this problem or challenge of rate of what they call radiant temperature asymmetry. So not only that the surfaces around your body are cool, but that they are cool on one side of your body and warm on another side of the body, or maybe cool on one side of the space and warm on another side of the space. This asymmetry actually leads to all sorts of negative perceptual effects, not only on the human being directly because of the radiant temperature asymmetry, but also because of the inevitable temperature stratification that happens within the space. So you can get cold air puddling and cold toes effect and all sorts of other negative perceptual effects inside the space when you have this type of asymmetry. And historically, one of the ways that the passive house standard has said that we combat this passively is by using badass windows. And if we use badass windows, that increases the temperature on the interior face of the window, therefore mitigating or reducing the asymmetry, the difference in temperature from one side of the body to the other. That can help improve thermal comfort within the buildings, decreases temperature stratification. So that's an excellent thermal comfort improvement that we can implement for the winter time. Many years ago, though, we were looking at this and we were thinking, that's great, that's really useful. But then we were presented with a series of cases, conditions, whatever word you want to use, that didn't quite match the scenario that I just described. So, what I just described kind of makes sense if you're like in a, I don't know, a hotel with like a big glass wall. Um, but you've only got one wall and the rest of the space is kind of opaque. But what happens if you actually have like glass around a corner? What happens if you have glass on two sides of your body? What happens if you have really tall glazing? So we were kind of working on projects that were presenting to us these interesting and I don't want to call them non-standard, but like let's say from a Pascal's perspective, non-standard conditions. And we were looking for different ways that we could assess and model the thermal comfort impacts of these types of kind of unique or non-standard conditions. We felt like that sort of basic Pascal's technique of just reducing straight asymmetry just wasn't quite sufficient for capturing the nuance of the actual buildings that we were building. So again, this is, I don't know, 5 or 6 years ago, 7 years ago. What we sort of settled on at the time, or one of our early attempts to add nuance to our modeling was to say, okay, what if we used some of these new computer systems and software tools that are available, which can harness the power of modern computers to calculate shit really, really fast. Right? So one of the things that the Pastos folks working in 2001 didn't have was an amazing Silicon M1 Apple or M4 Apple computer that can do thousands, trillions of these calculations very, very fast. But we do have those nowadays. And so instead of just calculating a single asymmetry value, what we can actually do is we can actually take into account the entire space around the occupant. We can calculate the temperature asymmetry across not a single value, but an entire mapping of values across a space. So what you see here is one of our early attempts to take that corner glazing scenario and model not a single temperature asymmetry value, but a range, a mapping of temperature asymmetry values across an entire analysis grid. We built up a whole kind of toolkit here to allow us to do that kind of modeling. The upshot, what we get out the other end is we get, again, not a single temperature asymmetry value, but rather a sort of a mapping of comfort effects or comfort perceptions within the space. So you can sort of see inside of this apartment here with the corner glazing, how the temperature asymmetry rises as you get closer to that corner glazing and falls off pretty quickly as you move deeper into the space. And so these types of modeling tools, which are, again, not replacing our passive house tools, but they are supplementing them and adding more nuance, adding more depth, adding more data, more information to the modeling phase and the design phase really help us to design better buildings, buildings that are going to be more comfortable throughout. We can identify hotspots for thermal comfort issues or thermal comfort problems, and we can attack those through design measures. This was an early effort to sort of, again, kind of supplement those fast house tools with more nuanced tooling and modeling assessment methods. So that's pretty interesting when it comes to the heating side, right? That's the heating side is important. But as I've said, and as again, I'm going to try and argue throughout this presentation, the cooling side is just as, if not more, important. So we also, in addition to that wintertime scenario, need a method of assessing summertime. And one of the nice things that ASHRAE 55 has that ISO 7730 does not is a method for calculating the comfort impact of solar gain on occupants. So this is a way of saying, okay, not only are we going to take the sort of ambient higher temperatures of summer into account, but we actually want to calculate the effect of solar radiation directly on a person's body when they're inside of a space. And so we can sort of take the idea, the sort of methodology that we implemented in the last example there, add in this new layer where we say, oh, let's take into account the sort of summertime effect of solar radiation directly on a person's skin. And now what we can see is if we apply that to, in this case, a different building. This is a kind of a small wing of a single family home out on Long Island. We can again see a comfort mapping, a sort of comfort gradient throughout the entire space, but this time really focused on those overheating risk areas. And of course, it's not really any surprise that the big south-facing unshaded expanse of glazing is going to be the area that you're going to feel the most discomfort when it comes to the experience of that space. Nothing revolutionary there, but at least we can put some numbers to it. We can quantify it. And once we've quantified it in this way, we can start to go through the design exercise of what if I do this? Does it become better or does it become worse? Well, what if I do that? Does it become better or does it become worse? Right? Those design exercises become informed by these types of thermal comfort simulations and mapping efforts. So that was interesting. I mean, that was many, many years ago. Those point-in-time assessments were useful. They were helpful. We felt like they were sort of adding something useful to our overall modeling within our projects there. So those point in time were good. But of course, we were curious and wanted to know if we could go a little further. So once we could get a handle on those kind of point in time, to be clear, right? Those simulations we were just looking at, those are looking at a single moment in time. How do we begin to play that out over time? So what happens when we start to look at maybe a week-long sequence of how our building performs? So this is an example of trying, not entirely successfully, but trying to start to apply some of those ideas to an example project. So in this case, this was a community center in upstate New York. I don't believe this was ever built, but this was 2018 or something. This was a study. And in this case, we were, of course, using those passive house modeling tools. As I said, those are critical. Those are super important. They're super useful. But we were supplementing them with additional dynamic hourly energy modeling using the Energy Plus platform. So in particular, the results I'll show here were focused on just one block. So with these other types of tools, we can end up or we have to zone the building into blocks rather than doing a big single zone model like we would do in Passive House world. And so in this case, the results I'll show here are for that highlighted volume there, just a single zone in this. It was a community center office in upstate New York. And what we chose to do for this one was, and this will kind of lead into some of the other work that I'll show in a minute. The Energy Plus is a very powerful tool. Sorry, if you're not familiar, Energy Plus is a hourly modeling tool, sub-hourly modeling tool. It's an engine. It allows you to do really sophisticated performance assessment models of buildings. And probably, to my mind, one of the biggest challenges of Energy Plus is that when you run it, you just get this absolute fire hose of data out the other end. And it can be like a full-time job just to like wrangle all the data that comes out and clean it and organize it and synthesize it and make sense of it. And so for this project, what we wanted to do was try and limit the scope a little bit. And we said, we're not trying to do an annual energy assessment using this tool. So what we really want to do is shrink the window of assessment down to like a single week. So we identified the worst week in this climate. And on this graph here, what you're seeing is 1 week of data, 1 week of data. So going from day one on the left to day or Saturday on the left to Saturday on the right, I guess. So a week of data. You can see in the black line there, the outdoor temperature being plotted, going up and down, up and down, up and down. Very cold over this week. And then what you're seeing in the red there are two different versions of the building that we were assessing. We were assessing a sort of code minimum or a standard baseline version, if you will, and then a improved, optimized passive house version of the building. And what you can see there is the large reduction in what we're plotting, which is hourly heating energy demand. So kilowatt hours per hour, kilowatts, heating energy demand is what you're looking at here. So you can see the way that the heating energy demand is strongly reduced when we go from code minimum down to the passive house version. And again, this was us trying to kind of work towards a more limited assessment where we could use some of these more nuanced tools, but not in a way that like overwhelmed us with an entire 8,760, hourly data points, but really narrowed it in on a specific scope. And what we chose for this was a 1 week assessment period. And that was actually reasonably productive. It's a sort of limited enough time span that like a client, stakeholder can kind of wrap their head around it. And you can display the data in a nuanced way. You can identify and see many of the interesting dynamics that happen within the space, but it's not so much data that you get like buried underneath it. So this was kind of one interesting way to look at it. Now, the important thing to note here is that we're not looking at thermal comfort right now. We're not looking at any of those human perceptual effects. What we're looking at in this case is heating energy demand, which is why I call this a kind of like a rough try. This was 5 years ago or something, 6 years ago. And so again, we'll show some sort of new versions that I think are a bit more successful than this. This is just another way of looking at the same data that we were just looking at. And this way kind of shows us something a little bit different. What we're plotting here are those hourly energy demand values, so kilowatt hours per hour. So kilowatt hours, sorry, there's a motorcycle outside. Kilowatt hours per hour value. And we're showing the code minimum version and the passive house version. And we're showing those values, those hourly values, not over time. So in the last one, we were showing it chronologically. But here, what we're showing those values are plotted as a function of outdoor air temperature. Plotted as a function of outdoor air temperature. So warm temperatures on the right, cold temperatures on the left. And you would expect that as the temperature goes down, as the temperature gets colder, those heating energy demand values would go up. And of course, that is what we see, right? So in both the passive house version and the code minimum version, we see that the heating energy demand values go up while the code minimum version also goes up. What we see is a marked difference in the slope or the rate of change between the code minimum version and the passive house version. The rate of change of the passive house version is much flatter, much lower than the code minimum version. It's an indication that the building you're designing is going to be much more resistant, is more insulated, for lack of a better word, from the outdoor environment. So the lower that slope, the better, more independent your building is functioning from the outdoor environment. By contrast, that code minimum version, where it's much steeper, shows a much more sensitive building, one that's much more subject to outdoor experience. So just another way to kind of look at the same data that kind of teaches us something about, how well we're doing with the design. Like, is it on track? Is it sort of heading the right direction? But of course, I've already kind of hinted at this. Is energy demand really the right value to measure in these types of assessments? No, I don't think so. And so that kind of brought us to a few years ago. And then what I want to show next is going to be a series of experiments utilizing the framework outlined by the new PHA Revive standard, moving away from energy demand and more directly towards some interesting thermal comfort metrics. So if you're not familiar with the PHA Revive standards, PHA Revive 2024 was released in 2024, and it's got all sorts of really interesting tidbits in there. I saw Al was in the audience, so shout out to Al Mitchell and everybody at PHA for all their awesome work on this. I'm a big fan. I think it's super interesting, and I think there's a lot of really great parts in here. There's a lot of parts that I'm still very confused about. So we're learning, we're trying. But for the last year, we have been really trying hard to wrap our heads around the resilience assessment methods, which are outlined in this standard, and make sure or test those methods out on a couple of the real projects to kind of make sure that we're understanding the nuance and how these things play out. This standard is for retrofits, and again, it has some really, really valuable and useful set of frameworks, tools for doing this type of resilience assessment. It has some rules and protocols around how to set up your building, how to set up the model, loads, schedules, and whatnot. It's got a really interesting method for adjusting weather data. So one of the things, we didn't really talk about this before, but one of the things that's a challenge is, how do we use historical weather data to actually model sort of future scenarios, future weather scenarios or future building scenarios. So it's got a weather data adjustment protocol. And then to my mind, probably the most useful thing is that it strikes a couple of like threshold lines. It says, this is what your winter habitability should be. And this is what your summer habitability should be. And by having those references, that's incredibly useful to us as modelers, because then we can look at our results and compare them to the reference and say, are we over or are we under? And just having that baseline, that reference is incredibly useful. There's some all sorts of other cool stuff in there around total life cycle CO2 present value cost, project management, sequencing. I'll let you kind of read through this at your leisure. It uses Energy Plus as its calculation methodology. So overall, again, I think it's a super interesting framework. This is not a talk about the Revive standard, though, but I just wanted to shout it out and note that there's some interesting tidbits here that I wanted to pull out. Now, just to talk through some of the sort of bits here that are going to be relevant to the results I'll show in the next examples. The framework here says that we should model a 7-day power outage. So this is kind of an interesting nuance or difference from the way that we were looking at previously, where we were saying, oh, model the heating energy demand. Here what they're saying is, no, turn the power off. What happens if there is no power and there's a terrible winter storm or a terrible summer heat wave with no power, and then measure the thermal comfort effect, the habitability of the occupants in your building during that scenario? There's a couple other things here. There's one interesting one, and maybe Al, I don't want to put you on the spot, but maybe he can help us understand this. I believe that the rule is that if you have an ERV or an HRV, you're supposed to run it at 5 CFM per person off battery power. Now, that's way beyond my sort of knowledge. I don't know anything about electricity and that sort of equipment configuration. I don't know if that's actually possible. If anybody knows how to do that, I'd be super curious. Batteries are not something I really have any experience with, and so that's a really interesting one. And that is how we set up all the models that I'll show you in the next sequence. But I'd be curious to know whether that's actually sort of feasible or realistic for projects nowadays, if they really have ERVs that are running off of batteries. I would also note, and again, this is maybe one of the places where I am a little confused by this protocol. It appears to say in the standard that if the building has a battery system capable of running the heat pumps for active cooling, then they can be used to provide active cooling. Again, that's kind of beyond my pay grade. I'm not aware of how heat pumps can be run off of batteries. I was under the impression that the startup voltage on those heat pumps was too high to run off batteries, but maybe that's no longer true. Again, that is way outside my sphere of expertise. So for all the examples that we're going to be showing, we are running the ERV, but we are not running the cooling heat pumps. So for the examples, cases that I'll show in the next little bit. Just briefly, one of the interesting things, as I noted, was that there's a weather data adjustment protocol here, which basically allows us to take TMY data, typical meteorological year data, which is a sort of averaged or smoothed out weather data for your location, and turn it into, let's call it stress case weather. So, you take your summertime week and then turn it into a heat wave as we show here. So this is plotting the results of that weather morphing or weather adjustment over time. You can see the original TMY3 data on the bottom, and then the adjusted temperature that's used for the simulations on the top there. Again, we're looking at just a week of simulation. So not looking at the whole year, but we're zooming in on a single week in the winter and a single week in the summer. And we're going to use this adjusted temperature data for our simulations. So this protocol is in there, and I think is a valuable piece of the puzzle here. But as I said, to my mind, the most valuable things are that we have these thresholds to measure our models against and say, oh, are we meeting these targets? Yes or no. So what are the targets? Well, in wintertime, what they say is that we should have, over the entire 7-day period, we should have less than 216 SET hours, standard effective temperature hours, below 54 degrees Fahrenheit. It's a little confusing. We'll talk about that. And then in summer, we have to have 0 hours per year, or per assessment period with a heat index above 102 degrees Fahrenheit. So, and then there are other rules, but those are kind of the main ones that are relevant to to what we're looking at here. So we have these kind of threshold levels. We say, oh, we want to go below in wintertime or above in summertime. This is some weird vocabulary there. Heat index and standard effective temperature. Standard effective temperature. Let's just call it a feels like temperature, more or less. Considers things like air temperature and surface temperature, importantly, relative humidity, airspeed, clothing, activity level. All of those things get taken into account when we calculate the standard effective temperature. The heat index is another feels like temperature, but this one a little bit more limited, takes into account humidity and temperature there. So a couple different ways of assessing temperature. We're not just looking at dry bulb air temperature, but we're looking, for lack of a better term, let's call it broadly, we're looking at feels like temperatures. So feels like temperatures for winter and feels like temperatures for summer. So let's look at a couple examples. So as I said, what we were curious about was what happens if we apply some of these methods and frameworks to some of our projects. Now, we're not certifying these projects to the Revive standard. These are actually new construction, so they're not retrofits, so they're not eligible anyway. But I like this method of assessment, or I was curious about it, and so we wanted to apply it and see what the results were. And so this is a small home, new construction, passive house in upstate New York, up in the Finger Lakes region. You see it's on a steep site here, wooded site, and it's a small house that kind of works its way down the hill a little bit. Not optimum surface to volume ratio, but passive housey, and certainly within the bounds of the types of passive house buildings that we do a lot of. Predominantly south facing. And you can see here, well, it's south and east facing. It's on the west side of a lake. And so there's a lot of glass on the south and east side, sort of pointing towards the lake there. And it was with the volume of glazing, whenever we see this much glazing on a building, your sort of spidey sense should sort of kick off and you should start to think, man, are we sure that it's going to be okay in the summertime? Right now, today, when it's 102 degrees in this place, is it okay in this building? Or are we designing something and optimizing for wintertime and not really paying enough attention to the summertime scenario there? One of the ways that we've done that historically is by calculating seasonal radiation values. On the right-hand side there, you can see radiation mapping across the windows, that looking at a seasonal radiation in terms of kilowatt hours. And you can see obviously those skylights showing up brightly, and then the other windows to a greater or lesser extent, seeing a pretty significant amount of radiation in the space. But again, we were curious what would happen if we applied these resilience techniques or modeling assessment methods from that Revive standard to this particular project. And so what we're seeing here, let's take a minute, we'll look at this graph because it's kind of interesting. So you're seeing time and you're seeing the SET temperature, so the winter time temperature that feels like temperature inside of the space. And you're seeing it over many days. So that cycling there is over the day. So it goes up during the day when you get some heat gain and goes down at night when you see a bunch of heat loss. So up and down and up and down and up and down across the entire period. You can see the power goes off on the left-hand side and the power comes back on the right-hand side. And we've got two different lines here. One of them, this was during a phase of the project when we were assessing different shading options. And so you can see here, there's a version with no shading whatsoever, and then a version where we were adding in different shading elements and site shading elements, trying to see the different effect. And you can also see that threshold temperature struck there at 12 degrees Celsius, 54 degrees Fahrenheit, where we're not supposed to drop below. Or rather, we're not supposed to drop below for a long time. So it's not that we can never go below that. It's that you don't want to dwell below that for a long period of time. How long is long? 216 degree hours, if you were to add up all of the period below there. Right, so that's kind of what you're looking at in this graph here. And it's interesting, right? So the power goes out, and for the first day, it's okay because we're getting a fair bit of solar radiation, kind of keeps the building warm. There is a pretty steep drop off. We lose a lot of heat overnight, but then the next day there's a lot more solar radiation, brings us back up, and then we lose a lot more. But notice what happens there on the January 22nd, the sort of middle of the day there, we have a very small increase in the temperature of the space there. In the weather file, that January 22nd day is a cloudy day, so we don't have a lot of solar heat gain. As a result, our temperature doesn't go up very much, but it does fall quite a bit, and then we fall into that sort of problem zone there. And so all of these different dynamics are playing out and affecting the performance of the building. And so we don't need to kind of dwell on anything here, but what I want to show is just, this is a way for us to get a window into, a view into how our building is performing in a different way than the annual energy modeling or the energy focused modeling really gives us, right? This is like a whole different perspective on what it's like to be in this building, and what the performance of this building is like. And because of the nature of the tools, we can sort of dive into any aspect of the performance here that we're interested in. In this case, we're looking at the total window heat gain, and you can see that cloudy day on the third day there. And you can also notice here how those heat gain values. So this is window heat gain. How those heat gain values are skewed to the morning because of the orientation of the building. You can see that we're getting most of our heat gain in the morning there. And so if we're designing shading strategies, this is the kind of data that you want to know when you're really dialing in effective shading strategies for your building. Now, when we flip the equation and we sort of take a look not at the wintertime, but rather at the summertime period, we see a different picture. So in the summertime, we do a similar thing where we say identify a peak week and we turn the power off, and then we let the building run for 7 days, and then we turn the power back on. And during that period, we have to make sure that our building does not ever cross over into that danger threshold area there, right? So we've got a couple of different kind of thresholds here that we want to make sure that we stay out of. And so what you can see here is, especially on, whatever that is, day 3, day 4, we're definitely seeing some spikes, some peaks where the temperature, this case, the heat index temperature, does cross over into that sort of problem zone, that danger zone. However, notice also that we're plotting 3 different variants of the building. So in this case, we're plotting a variant with no shading whatsoever. That's the blue line. A variant with building shading, so that's the red, building shading like awnings and things like that. And then the green is where we're adding more shading and adding in a bunch of site features. So one of the questions on this particular project was the level of tree clearing that was going to happen. Given the nature of the site and the nature of the existing tree canopy, what needed to get cleared to make room for the building, and then what was gonna get kept. And what we could clearly see is that by keeping those green highlighted trees, in addition to the red shading elements here that we're highlighting in this detail, we're able to drop those temperatures within the space pretty significantly. Whatever, that's almost 8 degrees Celsius of reduction there in those peaks. And at least in terms of this modeling, able to move us out of that danger period down into that warning period. It's still hot, it's still a heat wave, but we're definitely able to positively improve the performance of the building and make the case to the team that actually you really want to keep more of that existing tree cover than you thought you did originally. You want to hang on to that because it's really benefiting you overall in your total performance. So again, this is a way of seeing the performance of the building. It's very different than we see when we're looking just at that annual energy. Annual energy is important. We're not saying throw that away. What I'm saying is supplement it with these more nuanced and detailed types of models. And then just the last thing here, the last example here that I'll show is another one that we were trying out these techniques on. Is a townhouse down in New York City. Very different building, stratified building with many vertical zones. This one, again, kind of east facing, so challenging from a exposure perspective. But this one, by virtue of A, the fact that it's a townhouse, so it's sort of buffered on both sides, and B, that it's in New York City, which is a much warmer climate than upstate New York. You can see here that there's basically no problem at all when it comes to winter performance. So you're looking at the wintertime SET temperature here. Notice the threshold temp is way down on the bottom of the graph. We never even get near it. So when it comes to this building, and this gets borne out in our experience with these townhouses in New York City, There's almost no challenge at all when it comes to the wintertime performance. If you implement all of those passive house strategies, lots of insulation, good air tightness, and ERV, you're going to be fine when it comes to your wintertime performance. However, if we flip the script and we look at the summertime performance, those same things which helped us in the wintertime start to penalize us in the summertime. So it's a warmer climate, it's a denser climate, it's a more tightly packed project. Um, um, and so what we're seeing here is, again, the summertime power outage period. And notice here that all of our values are climbing up into that danger period quite significantly. In this case, we zoned the building into multiple zones. And so you're looking at the different lines represent the different floors of the building. So, you know, the cellar and the first floor and the second floor and what have you. So you can see the different floors independently. And obviously each floor is going to perform a little differently based on the amount of glazing and the internal temperature stratification and what have you. And so this was really interesting, and this was definitely an important flag for the design team to say like, whoa, we have not focused enough on the summertime performance here. And so we really need to go and dive in and figure out how we can improve that summertime performance. We kind of appear to have the wintertime thing sorted out. That seems to be working really well, but clearly these methods are indicating that we have a problem in the summertime. And so I think from these types of results, it appears that the design up to that point had been too focused on meeting those heating targets and not focused enough on meeting the cooling targets. Again, I am not arguing that we should ignore the heating targets. What I'm arguing is a both and. We should meet all those heating targets, and we need to focus as much effort and attention on the cooling side as well. Again, because of the nature of the tooling here, we can really dive in to a super fine level of detail. And we can say, oh, look, those peaks are happening at 8, 9 o'clock in the morning, and depending on the floor. And so again, as we go back and we work through the design phase and we say like, oh, okay, we need to design better shading. Well, what does better shading look like for this building? Well, clearly it's going to be shading that's going to attack that early morning sunlight in this particular building with this particular orientation. And so this kind of data helps focus our efforts as designers when we start to do things like, oh, we need to design better shading for our building, right? And yeah, of course, now that you say it, if you looked at it in plan, you would have said, yeah, you need to have better shading on that southeast face. But again, these methods are just ways of helping us see things that already exist in our building, and just bringing them to the fore. They're just showing them to us in a new way where they're harder to ignore, harder to mistake, and then we can attack them and design them to work better. So my recommendation is, at a minimum, supplement your passive house models with a detailed hourly simulation to assess reheating performance during summer. I really like this idea of doing a summer power outage assessment. I think that's a strong idea, and I think it will really help us to design better buildings. If you have the capacity, do a winter one as well. I think the winter one is maybe a little less necessary than the summer one, though, although I'm open to being wrong about that. But at the minimum, I think the summer one could really help us design better buildings. Now, if you're interested in learning any more about any of that, I know that was a bit of a whirlwind. Just a last shameless plug here for the Reimagine Buildings Collective. If you are not already a member of the Reimagine Buildings Collective, head over to the Reimagine Buildings Collective and you can join up. We are a group of professionals who are working to design and build the best buildings we possibly can and share knowledge amongst one another. As part of the Reimagine Buildings Collective, we've been rolling out a whole series of members-only video tutorials. So if you're interested in learning more about PHPP modeling or some of this dynamic energy modeling with Energy Plus and some of the other tools that we're using here, you can head over there and join up and get access to those members-only video tutorial series if you're interested in any of this stuff, or if any of this seems like it would be valuable. In fact, we this summer are going to be rolling out another cohort through our Honeybee PH modeling series, where you learn the ins and outs of Rhino 3D modeling, grasshopper modeling, honeybee modeling, which is a toolkit for making Energy Plus models, and then the honeybee PHA toolkit, which allows us to export and push the data from those Energy Plus models out to PHP and Woofy passive. So if you're interested in any of that, you can, again, head over to Reimagine Buildings Collective and take a look at that if you're interested. So that was a really long, that was really long. I hope I didn't go over too much. Maybe we have like 2 minutes for questions, but I will leave it there. Hopefully that was of interest to folks.
So with that, let's dive into the first question. So that is from Keith Sharp. So Keith, if you're here, please ask away.
Okay, can you hear me?
Yes.
Okay, yeah, my first question was on what weather data was used. It looked like you were using TMY3 weather data. And my comment is that typical meteorological year kind of averages things and is generally not a very good representation of extreme weather events, which would be relevant to resilience.
It's a good point, Keith. Yeah, and I mentioned it briefly. It is TMY3 data, but one of the nice things that that new revived protocol has is a methodology for taking into account the peak temperatures from the ASHRAE data and then modifying, adjusting, changing the TMY3 data so that it more accurately represents a peak or extreme condition. So it is not, in those last examples I was showing, it is not straight TMY3 data. It is adjusted or modified data, taking into account those extremes. So that's yeah, that is an interesting nuance to the whole modeling approach there. It's a
Yeah,
great point.
something that you might want to consider is that recently I've developed what I'm calling ambient meteorological year weather data. And so far, I've taken the 26 years of archived weather data that's available from the National Solar Radiation Database and run a dynamic building model for all 26 years and identify the most extreme winter and the most extreme summer. And then if you put those two seasons together, then you have an extreme weather data set that is going to give you the lowest indoor temperatures and highest indoor temperatures throughout those 26 years. And I think
That's
it's
cool.
really useful for evaluating resilience.
Yeah, if you have a link for that, maybe post it to the chat if you'd be willing. That sounds cool.
Yeah, I have a published paper on it and another one that's in the works. So it might be useful for you.
Absolutely. No, it sounds great.
Fantastic.
No, thanks
Thank
for
you, Keith.
sharing.
Yeah, yeah, that's fantastic. So Sherry, you're looking for some help with Design PH. Do you want to pose your question?
Well,
Or
I just downloaded Design PH on Monday, and I have a project I'd like to, or a couple projects I'd like to use it on,
Uh-huh.
but I realize I'm going to need some help, like a consultant or something.
Sure.
So, any ideas where I can find one?
It is always challenging. Yeah, I mean, there are definitely, any CPHC who works to the PHI standard nowadays in the US is probably going to be facile with Design PH. There are not very many good learning resources available for Design PH right now. There's a couple, but they're spotty. There's one video course that we did many years ago, but it's all in metric units because it was for Passwest Canada. And so, boy, I don't know. What do you think, Zach? Are there any resources we could point Sherry towards? I'm drawing a blank, to be honest.
yeah, I am
But
too. I would definitely invite people who on the call to share in chat. Yeah, Sherry, we'll do some thinking on
Maybe,
that
yeah,
and
maybe
get,
if you want
yeah.
to follow up with us offline, we can connect with folks in your region. I'm not sure where you're based, but maybe you can email us or text us, get in touch with Zach or I, and then we can kind of see who we can find in your region that could help you out for sure.
That sounds great. And if
Totally.
anybody out there is listening and has this, I'm in Seattle, but I'm used to working with people all over the world. So it
Okay.
doesn't, yeah. So, okay, well, thank you.
Sure, sure, sure. I'm sure
Great.
we can find somebody to hook you up with for sure.
All right. So next up is Eric Zeiss.
Hi, Ed. Hello,
Ed.
Ed.
Hey, Eric.
A couple of little quick little small things. You had put down the limits that were set in the some number of hours under 54 degrees Fahrenheit, and I seem to remember a huge number there, and
For the, you're talking about the set
more than
temperature for
7
the winter
days.
time?
It was more than 7 days of time below 54 degrees
Those
in
are,
a 7-day
I think,
period.
I think Al addressed that in the chat too. Those are degree hours. So it's an
Oh,
hour
perfect.
multiplied by the degree of delta, the degree of
Delta.
difference, if that makes
Beautiful.
any sense.
Okay,
It's
now I understand.
the area between the curves, essentially,
Got it.
is what you're
It
trying to
makes much
calculate
more
there.
sense now.
Yeah.
And the other little nit, I suppose, was in your summer graph. Oftentimes, it's cooler in the nighttime than in the day. So, opening windows and using active cooling through fans would be a way to bring things down to a potentially useful or more useful temperature, so that it doesn't get up into that really dangerous area. So, just a thought
It's true
on monitoring
sometimes,
that.
but it is not always true. I mean, it is not true in New York City right now, right?
Right.
It has not been true for the last 5 days that it has cooled off at night. Instead, it has actually stayed incredibly hot at night. So it's not unheard of that it actually stays very, very hot overnight. And I think that's the case that's trying to be captured here, is that really extreme case. Now you could I definitely think you could say like, oh, maybe we could try this again with like a slightly more moderate case and see what the results would be. But this, what we're showing here is the kind of like the extreme case where it's like, oh, well, what happens if it's 80 degrees Fahrenheit all night long? Then you can't open the windows. Then you're stuck. But you're right. Like there's another version where it's like a more modest temperature, and that would be really interesting to see what the effect is, because you definitely can and should model the opening of windows into your building and sort of try and take into account that effect, and when it's beneficial.
So,
It's definitely climate dependent, right? I mean, I was in northern Spain last week, and it was 100 degrees during the day, but it cools off to 50 degrees at night. And so, yeah, in climates like that, desertish climates like that is going to be a hugely useful technique to open up the windows at night. But a place like New York City, it's not at all. So it's going to be very climate dependent.
and another source of cooler air is basement.
Yeah, that's true. That's a good point.
Or elevator shafts. Just thoughts.
Excellent.
Yeah,
Yeah,
no, that's
no.
a good point.
Thank you, Eric. That brings us to the close of questions so far. Both Jessica and Eric had to leave the meeting. So if there are any other questions, we can entertain them for a moment here. I really appreciated this presentation, Ed, and I'm also really excited about the Revive approach and the focus on resilience and carbon, both embodied carbon and operational carbon, that it brings to just helps bring to decision making around retrofits and what intervention makes the most sense. And to your point about the extremes, like, I mean, with the heat dome in Portland, Oregon, which is in the Pacific Northwest, it's not a hot place typically. The heat dome here in Portland hit 114 degrees Fahrenheit. So just so far out of the norm that I think it is, and also to Keith's point about really figuring out how to look at the potential of serious extremes, and then have that help guide our approach to building. It's just is super important, super relevant. It's kind of a unlucky or lucky happenstance that this presentation happened during the heat dome on the East Coast. It doesn't look like we have other questions right now, so I want to thank everybody for joining us for this season finale of Passive House Accelerator Live. We will be back in early September with the 2025-26 season of Lives. And meanwhile, the Reimagine Buildings Collective will be very active during the summer, so join us there.
Fantastic, fantastic, and great to see everybody. And thanks again for the invitation. Yeah, we should have Al back on in the fall to really dive into the Revive standard and explain to us all the ins and outs of it.
Absolutely,
you're tapped now, Al. So
yeah, definitely.
So again, great to see
have
everybody,
to
and
persuade you.
thanks for the invitation to be here. Good to see everyone. Have a great summer.
Thanks so much, Ed.